refresher, can someone describe the product rule shortcut for us? Another way to find a derivative of a function? Maybe the little phrase we used yesterday? 1d2 plus 2d1. Okay, so when you are multiplying two things together, you can go through the product rule shortcut to help you find the derivative. Okay, so it's always about multiplication. We were working on the bottom of page 140 trying to figure out the equation of the tangent line. I believe we found the derivative, but that was about it. We didn't find the point or the slope yet, right? Can someone help me out? Did we tackle the point or the slope yet? I don't think we did either. Okay, so this was our derivative that we ended with yesterday when we went through the product rule on the g of t function they gave us, 1d2 plus 2d1. We got to figure out the equation of the tangent line at this spot of pi over 6. So we got to figure out the point, aka y value, at this spot. We also got to figure out the slope, aka derivative, at that spot. So maybe we'll tackle the point first. We're going to plug in pi over 6 into the original equation. Now we're dealing with trig, and pi over 6 is a spot on the unit circle we have to know. It's in the first quadrant. All right, so let's see what happens. Pi over 6 squared. Can we simplify that? What happens when you square a fraction? Or think about it as pi over 6 times pi over 6. How do you multiply fractions? Let's see, pi squared over 36, right? You square the top, square the bottom, okay? Unit circle time, cosine of pi over 6, aka the 30-degree spot. Good. Okay, so multiplying those together, multiplying fractions, we go straight across the top, straight across the bottom. There's our lovely point. We'll leave it like that. You could type it into your calculator, get a decimal value, but notice how it can be done without a calculator. Okay, we'll just leave it like that fraction. Let's go ahead now and tackle the slope. So we're going to plug the pi over 6 into the derivative we found. All right, so we have negative pi over 6 squared times sine of pi over 6 plus 2 times pi over 6 times cosine of pi over 6, ton of pi over 6's. All right, so we already did pi over 6 squared. We said that was pi squared over 36 times the negative out front. We'll make it a negative. What about sine of pi over 6? Okay, if the cosine we said was a square root of 3 over 2, what's the other related ordered, or the other ordered pair value from that spot? The sine value? Yeah? The 1/2. Okay, so then we're going to add 2 times pi over 6. That's the same as pi over 3. The 2 over 6 can simplify. And we already said cosine of pi over 6 was square root of 3 over 2. So it looks like the slope value is negative pi squared over 72 plus pi square root of 3 over 6. Okay? Now you could add those fractions together, right? We could get a common denominator. We would have to multiply this fraction by, I think, 12 on top and bottom in order to match the 72. Okay? But we can leave it like that. I'm running out of room, so I don't really feel like doing that, to be honest. Okay, looks weird. It's still representing a slope, though. Okay, so somehow we got to bring together this crazy point value and this crazy slope value and write our equation. So we need y minus the point. I'm running out of room. Sorry, guys. I'm going to write it up top. Y minus the point equals the slope. Now, if we leave it as the two fractions, we have to make sure that we represent that the slope includes both of those fractions. So we're going to group them in parentheses. Okay, so y minus the point equals the slope times x minus your tangent spot. Note to self, more room for next time. All right, craziness, but still able to be completed. Just got to be familiar with your unit circle. All right, we're going to do more with the product rule today. Practice, practice, practice. 1d2 plus 2d1. Okay. Yesterday, we kind of saw how the product rule might not be needed every single time. Remember, if you're multiplying two polynomials together, you can expand them first and then use a power rule. Okay, so a product rule might not be necessary, but sometimes it's your only option. That's why we have it. So on page, I think it was 140, if you look back, we were asked to find the derivative applying the product rule. So we're going to go ahead and write down what we got from that response. So I think on page 140, the last page, we're looking at the top right-hand corner. Is that right? Okay. So we'll say it was labeled G on page 140, but I guess we're labeling it F now for some reason. So the derivative we said was 5 halves x to the 3 halves minus 9 halves x to the 1 half plus 1 over x to the 1 half. That was using the product rule. 1d2 plus 2d1. Okay, but if we look at this function a little closer, okay, isn't the square root of x technically considered like a polynomial? Can't we rewrite that as x to a power? Right? Wouldn't that be x to the 1 half? Okay, so if the square root of x is technically considered a polynomial and we're multiplying another polynomial, specifically a quadratic, maybe you didn't want to go through the product rule like we did yesterday. If you're multiplying two polynomials together, you can distribute them, okay, get rid of those parentheses. So let's see what would happen in this case. We should still get the same derivative because we're, again, using the same function. It's just a different method or process on how you want to go about finding that derivative. So let's distribute in that square root of x, aka x to the 1 half power. We're going to rewrite the original equation. If you're multiplying the same base, what do you do to the powers? Add them. Okay, so we need a 1 half times a 2. I meant add. I'm sorry. Add the 2. 1 half plus 2 is 2.5, but 2.5 as a fraction, you can write as 5 halves. You don't really see decimals as fractions. That's why we normally write them as or you don't normally see decimals as exponents. That's why we write them as fractions. If we went on to the next term with that distribution, we would need a 1 half plus a 1. So that'd be 1.5. But as a fraction, that'd be 3 halves. And then the last distribution to the 2, we would just have 2x to the 1 half. So instead of now multiplying two different pieces together, we physically went through the multiplication, we reduced it, we simplified it. Let's use the power rule this time. Okay, that first shortcut that we learned. So we can bring down the 5 halves, and if we drop 1 from the power, we'd have 3 halves. In the next term, if we multiply down the 3 halves, times 3 would give us 9 halves, and then drop 1 from the power, we'd have 1/2. And for the last one, multiply down the power, we would just get 1, and drop 1 from the power, we'd have -1/2. So do you guys see how it is the same thing? Okay, we would just have to rewrite the last term. If you have a negative power, you can move it to the bottom to make it positive. Okay, they match. So you have options when it comes to the product rule, but only if you're multiplying polynomials together. Okay, if you're multiplying by a trig function, you're kind of out of luck. Or an exponential function, a log function, we're eventually going to get to those, you're kind of out of luck there. It's only polynomials. Okay, so what do you think should be learned here? What's the lesson to be learned from what we did? Do we have a preference of one over the other? Do we prefer to expand it and then do the power rule? Or do you guys like that product rule initially? Do we have a preference?
I like the product.
You like product, like initially and then simplifying?
Yeah.
Some people might like simplifying and then doing power. Okay, you have options. So we'll say if 2, we'll say plus, okay, because maybe you're multiplying more than 2 things together. We're going to check that out in the next example. If 2 or more polynomials are being multiplied together, you could expand first, then use the power rule to find the derivative. Okay, I'm not going to say one way is easier than the other. Okay, it's always a personal preference. It's always kind of based off the difficulty of the 2 polynomials. It's just which one you feel more comfortable with. Okay, so again, you have options as long as they are polynomials. Okay, x's to powers. So speaking of this idea of polynomials, maybe you're multiplying 3 of them. Okay, take a look at the last one. We have 2x plus 3, which is linear, times an x minus 1, which is linear, times an x plus 3, which is another linear. So if we were to multiply all those together, what would our function be? Linear times linear times linear? Cubic, right, okay. So here's the thing. Some of you said you're more comfortable with expanding. Okay, we can definitely multiply all those together. Some of you said you were more comfortable using the product rule. What's the issue, though, with using the product rule with this function? We are multiplying things together, but what's a little different? If you think about our product rule phrase, 1d2 plus 2d1, that was only if we had 2 things being multiplied together, and this time we have 3, okay? So let's see how we can tackle this, okay? We're going to try 2 different methods, again, just so you realize you have options, okay? We're going to do the expand way, okay? But then we're also going to try the product rule first. So do you want to expand first, then take the derivative? Or do you want to take the derivative and then expand, aka simplify? Let's try the expanding one first, because I want to take some time to talk about the product rule if you're multiplying 3 things together. So, if we were to expand this, going through a FOIL process on the first 2 terms, we would have 2x squared minus 2x plus 3x, so that would simplify to plus 1x. And then a minus 3. But we still have to multiply in that third term, okay, that third quantity. So a little bit more distribution to be done. And looks like we have some like terms. The 3x's are actually going to go away, which is nice. All right, can we expand that correctly? Kind of distribution on steroids. 2x cubed plus 7x squared minus 9. Sound about right? Okay. So now that we expanded it, let's go ahead and take the derivative using our power rule, because we have polynomials, we have x's to powers. Looks like we'll get 6x squared plus 14x. Sound good? All right. Let's go ahead and try the product rule. Okay, maybe you didn't want to expand those, go through all that distribution initially. Well, maybe you wanted to go straight to the derivative. Okay, now when we were multiplying two things together, we had that phrase 1d2 plus 2d1. But in this case, we're multiplying three things together. So what I'm going to do is kind of write a general three product rule here. Maybe we'll use h, j, and k to represent the three functions. They're having fun over there.
I'm having more fun.
I hope so. I hope so. Okay, so can we think about this? Dan kind of said something yesterday, if we remember it or not, that kind of clued us into how a three product rule might work. Instead of 1d2 plus 2d1, can we think of a similar phrase or a similar setup for three terms? So as a refresher, Dan yesterday was wondering, is it always 1d2 plus 2d1, or can you kind of rearrange the way things are written? Okay. Think about how we can maybe apply that to a three product rule. What do you think?
Couldn't you just have like jx times kx and get like, instead of a hjk, you get a hl or something, so that way you get it down to 1d.
You're going to throw in another function? You're going to throw in an L too?
Well, no, just
No.
have j and k, or h and j combined. Combine two of them.
Oh, okay, so you're saying take this one times this one, multiply together to get L, a new
Yes.
function, and then do L and K in terms of the product
Yes.
rule. You could do that. Okay, you could turn 3 into 2. Didn't we do that here? We went from 3 quantities down to 2 quantities. And couldn't you use the product rule on that quantity and that one? Because we now have 2. Okay, that's a possibility. Let me ask you this. What if they weren't polynomials? Okay, what if you couldn't multiply them together? For instance, what if we had sine of x times cosine of x times tangent of x? They were all trig functions. Okay, I know we haven't talked about the derivative of tangent yet. We'll get there. But what if you can't expand them? We're not going to cry. That's not one of our options. Okay, so let me think about this. We said if we were multiplying two things together, for instance, f of x and g of x, then the product rule was 1d2 plus 2d1. You don't have to write this down. I'm just trying to make a note here. Do you notice how the product rule is a combination of keeping one function the same and then multiplying by the derivative of the other? And we're just adding those combinations together. Like, for instance, we keep f, but we times the derivative of g. And then the other combination would be keeping g, but multiplying with the derivative of f. Okay, and we're adding those together. So if we think about that combination, what combinations can we get when we have three things being multiplied together? In this case, we're going to keep two of them the same times the derivative of the third. What would those combinations look like? You want to keep h the same? Keep j the same? That means we'd have to multiply by the derivative of k, which we could label as k prime. Let's go ahead and add another combination. Keep two functions the same times the derivative of the third. You want to keep j the same and k the same. We then have to multiply by the derivative of h. Is there another combo? Keep h the same and k the same. We'd have to multiply by the derivative of j. I think that's the last one, right? Do you think you could develop a product rule if you were multiplying 4 things together? 5 things together? Yeah, okay. Okay, so a product rule, we are going to think about it as 1d2 plus 2d1, okay, because on the AP test, they're not going to get more than 2, okay? But notice how you could go more than that if you needed to, okay? Let's see how this works. Okay, we're going to apply it here. So let's check out the derivative. We have our 3 quantities. So we got to do the combo of keeping 2 the same times the derivative of the third. So maybe we'll keep the first 2 the same. What's the derivative of the third quantity? 1. So times 1, you don't have to write it if you don't want to. Let's go ahead and add another option. So keep another 2 the same. Maybe I'll do the 2x plus 3 and the 3, or x plus 3. So then I would need to multiply by the derivative of x minus 1, which is just 1 again. So you don't have to write it if you don't want to. And then the last combo would be keeping the last 2 quantities the same times the derivative of the first one, which would be 2. So that one we do have to write. Okay. Now we still have some cleaning up to do. Okay, but we're going to expand it. We're going to get rid of those parentheses. Okay, so FOIL process on the first 2. 2x squared minus 2x plus 3x would give us an x, then minus 3. We'd have another FOIL process on the next 2. 2x squared plus 6x plus 3x, so that would give us 9x plus 9. And then FOIL, bless you, FOIL process on the last 2 and then double all of your terms. We're multiplying by 2. So x times x doubled would give us x squared. 3x minus 1x would be 2x. Double that, we get 4x. And then negative 3 doubled, we'd have negative 6. All right, like terms. 2x squared, 2x squared, 2x squared. We got 6x squared. Plus x plus 9x plus 4x looks like 14x. Minus 3 plus 9 minus 6. Cancel out. Okay. Notice how our derivatives match. Okay, so you have options. Again, these were polynomials, so you can either expand and then do the power rule, which seems a lot simpler, okay? But you could initially use the product rule. This time it was 3 items being multiplied together, okay? Now, we didn't really answer the question yet. I was getting ahead of myself looking at the derivatives or the options here. If this is our function, what is the slope of the normal line when x is 2? Okay, so now that we know what the derivative is by using either process that you're more comfortable with, how might you find the slope of the normal line? At 2. What are you going to do, Braden?
Just plug 2 into the derivative and then find the opposite or so.
Okay, plug 2 into the derivative. That would give us the slope of the tangent line. And then we got to opposite reciprocate that for the normal. Okay, So we have 6 times 4, which is 24, plus 28. Looks like we got 52. So opposite reciprocal, we get negative 1 over 52, slope of normal line. Okay. Again, I don't expect you to remember the product rule for 3 terms, but do we at least see or understand where it comes from? Bless you. Okay, so you could do 4, you could do 5. It's just a combination of keeping all of them the same except one of them, and that's what you find the derivative of. Okay, let's go ahead and try some more product rule. This time we're going to relate it to some graphs. These are good ones. Okay, below are 2 functions, f and g, and we're specifically going to let the p function represent the multiplication of these 2 graphs together, okay, f times g. They're also giving us another function r, which is described as the multiplication of x squared times g. Use the graphs to answer the following questions. Okay, so in our first block, if the derivative of the g graph at -4 is 2, what is the value of the derivative of the p function at -4? Okay, let's go ahead and think about what we're trying to find here. The derivative of p at -4. Can we figure out the generic derivative equation for p? If we write down what p is, okay. Notice how p is f times g. Can you find the derivative of 2 things being multiplied together? What would it look like? I know we're using functions now, not necessarily equations. So if we did 1d2 plus 2d1, f of x would stay the same, times d2, so that would be g prime, plus 2, which would represent g of x, times d1, which would be f prime. We saw that yesterday, right? 1d2 plus 2d1. So if that's our derivative, and we're trying to figure out what's the derivative at -4, what do you guys want to do? What are we going to do with the -4? Yeah. Yeah. Can you tell me what we're going to do with the -4 first? No. Plug it in for x. Notice how, okay, that -4 took the place of that x value. All right. So, can we figure out f of -4? Yes. What are we going to do? Do we know anything about f? We can use the graph. If you were to plug in -4 as the x value into the f graph, what would you get out? Can you tell? You get out -1. Good. Okay. Do we know what the derivative of the g graph is at -4? Yeah.
0.
How'd you get that?
From the graph.
Let's see. So, 1, 2.
Oh, wait. No, I did that wrong. I did 4. Never mind. That's crazy.
All right. So, it's okay. If you were to draw a tangent line there, that would be an approximation, right? Because it depends on how accurate your tangent line is. Did they give us something specific? Do we know exactly what the derivative of g is at -4? Do you see how it was mentioned previously? They're telling you it was 2. So you could use the graph to approximate it, okay? But if they're giving you the exact value, that would be a little bit more accurate. All right, let's go ahead and move on. Can we figure out what g of negative 4 is? If you were to plug negative 4 into the g graph, what would you get out? Looks like 6. Does that sound about right? And then what about f prime of negative 4? Okay, now they didn't give us any information about that, so we must be able to figure it out based off the graph. If you go to the negative 4 spot and draw a tangent line, notice how the tangent line would actually kind of fall on the line itself. So what is the slope of that line? Can we figure it out? If you were negative 1, yeah, if you were to pick 2 points and calculate the slope, you'd get negative 1. Again, you can pick a point before it, pick a point after it. Didn't we say that the slope of a tangent line is approximately the slope of a secant? Okay, so it looks like we get negative 1 that way also. So negative 2 minus 6, looks like we get negative 8. There we go. So a little different type of type of question, still utilizing the product rule, but this time we're analyzing graphs and function values to help us get our final derivative. Okay, let's go ahead and try the next one. R of negative 2, or R prime of negative 2 is 20. What is the value of the derivative of g at negative 2? Maybe we'll start this one off similar to how we did the other one. Okay, at the top, they give us the R equation, just like we started with the P equation. Can we figure out the derivative of R? After all, they are giving us some information about the derivative at a specific spot, so maybe knowing the derivative would be useful. Can we go through our product rule because we're multiplying two things together? 1 d2 plus 2 d1. Are we doing okay? Make sense? If our goal is to figure out the derivative of g at negative 2, notice how that x value or special spot we're looking at graphically is negative 2. So let's fill in negative 2 for all the x's. Every single one. All right. So if our goal is to figure out g prime of negative 2, okay, that's kind of showing up on the right-hand side of the equation, we should be able to figure out every other value except for that one. That way we can solve for it. So we should know something about r prime of negative 2. Can we find that information either based off the graph or based off of something they told us? Do we realize that's 20? Okay. We can simplify negative 2 squared, that would be 4. We have no idea what g prime of negative 2 is because that's what we're trying to figure out after all. Can we figure out g of negative 2? Either off of information they gave us or the graphs that they provided. What do you think? You guys thinking negative 3? Is that all right based off the graph? Okay, So we have 20 equals 4 times the derivative we're trying to find plus 12. Okay, we're going to solve for that derivative, aka subtract the 12 over, you'd get 8, divide the 4 over, looks like you'd get 2. So the slope of the g graph at the -2 location is 2. So if you were to plot a point there, roughly draw a tangent line, it'd be a slope of 2. Looks like about right if you were to check your work. Okay, we doing okay? All right, let's check out the bottom ones. Find the equation of a tangent line to the graph of P at the x location of -4. What information do you need to know to write the equation of any line? I'm going to beat it into you this year. Point and a slope, okay? Maybe beat isn't the most politically correct word. All right, so we need to plug 4 into the original P equation, and we have to plug 4 into the derivative of the P equation. Do we already know one of those values? Didn't we do something like that above? Yeah? -8. There you go. So there's our slope, okay? But we do have to figure out the point value. So the P equation was defined as the multiplication of the f and g graph. So if you were to plug -4 into f and then -4 into g and multiply those values together, what would you get? Let's see, f of -4 looks like -1, and then g of -4 looks like 6. So -1 times 6, we get -6. So equation of tangent line, we got y minus the point equals the slope times x minus your tangent spot. Alrighty, let's try the next one. Same deal. Find the equation of a tangent line to the graph of R at the x location of -2. So point and a slope. Point comes from the original function. Slope comes from the derivative. Do we know either of those two values? Was one of them or maybe both of them previously provided? Who knows? What do you think, Ariana? The derivative is equal to 20. Yep, that was the information from the box above it. Okay, r prime of -2 is 20. We can figure out the point though. They did give us the r equation. That was x squared times g. So we're going to plug in -2 for those x's to figure out our point or y value. So we have 4 times, let's see, g of -2 based off the graph is -3. So it looks like we get -12. So point and slope, we can do y minus the point equals the slope times x minus your tangent spot. Nothing new, right? Okay, we're just approaching the same type of problem from a different angle, this time using product rule shortcuts to help us figure out the derivative. Okay? We're going to stop there for today. If you take a look at the next page, though, more practice. Okay, getting used to product rule functions. This time, though, we're going to take a look at a table, whereas what we did today was more graphical in representation. Okay, so just approaching it again from different angles. Product rule, do we like it? Shortcut? 1d2 plus 2d1.